Hello everyone, welcome to day 15 of our machine learning masterclass internship, and I welcome you all. So in the previous session we have discussed about algorithms, which is nothing but our linear models. So in linear models we have elaborately seen about our linear regression, then lasso ridge, and then about logistic regression, and we have wind up our yesterday's class. So in today's session, or in this session, what we are going to do is we are going to see a lot of algorithms in today's class, and we will be starting with support vector machines, both classifier as well as regressor, and we will be seeing about decision tree algorithms, which is a tree based algorithm. We will be seeing about classifier as well as regressor and decision tree, how they work, and then we will be moving into ensemble algorithms in today's class. When we talk about ensemble algorithms, we have bagging techniques and boosting techniques in that. So don't get confused with these new names. We'll be seeing about what those are just simple terms to represent their activity. And in bagging, we'll be seeing about some algorithms, random forests. We will be seeing about both classifier as well as regressor. And we'll also see about boosting techniques, and we'll be covering about ADA boost and XG boost algorithms in today's session. So these will be the agenda for today's class. And once again I welcome you all to this session. So talking about these algorithms, we'll see today's class will be, or this class will be more theory based. We won't be having much interactive hands-on session, because before going into hands-on is nothing but you can just import the library names and then use it. But if you want to learn the basics of what is happening behind it, what's the math behind it, then we need to have this mandatory theory session. So this will be completely a theoretical session about what happens in the backend of an algorithm, how a machine learning algorithm, this particular algorithm works. And I'll also tell you how to import it. We can go hands-on for that. What's the command to import it? And so the next class, day 16, will also cover algorithms. We'll be having about algorithms such as naive Bayes classifier, regressor, and then we'll be seeing about k nearest neighbor algorithm. And if you see, we are seeing a lot about supervised learning algorithms. In tomorrow's session or the next session, we will be seeing about after seeing our naive Bayes and KNN, we'll be moving towards our clustering algorithm. K means clustering algorithm for unsupervised learning will also be covered in the next class. After that, in day 17, we'll be seeing about hyperparameter optimization and then model evaluation part. So with that, in day 18, we can comfortably start our machine learning project. So without any delay, we'll get started and start our class with our first algorithm in today's class, which is going to be support vector machine. Talking about support vector machines are a popular and powerful supervised learning algorithms which can be used for classification as well as regression analysis. But I wish to tell you that support vector machine is mostly preferred for classification problems. We'll be mostly dealing with classification problems. It's not that much preferred for regression analysis, but you can. Okay, it's not built for regression, but it has been modified later on. So the main task for a support vector machine is classification. And that too, classification, when you talk about classification, you can use it primarily for your binary classification, which is yes or no, two class classification, right? So you can use it for that. But if you ask me whether can I use it for multi-class classification, should I not use that support vector machine for multi-class classification? No, not like that. It is possible, you can use it. Once again, what it will do is it will follow our one versus rest, like what it has been happened in logistic regression. So in previous class we have discussed, right? In logistic regression, what the algorithm does. So if you have multi-class, then it will decide at a time, it will select one class and then consider the remaining as the opposite class. So once again, it is converting it into a binary and go with the format of one versus rest or one versus all. So the same way support vector machine also go with multi-class classification. But if you ask me, this guy support vector machine performs very well when it is used for a binary classification problem. It gives the best. Okay. So talking about support vector machine, they are based on finding the hyperplane. Okay, we are going to find the hyperplane, which is a plane or a line that best separates the data into different classes. by maximizing the margin between the hyperplane and closest data point. So we are dealing with some names which is called as hyperplane, okay, and we'll be dealing about support vectors, etc. We'll see that what it is. So once again, support vector machine is a very versatile algorithm which can handle both linear and non-linear data set. Talking about linear and non-linear, I'll give you with example. So in your data set, if you are going with regression or classification, you can't expect it to be linear. So what if you don't have any idea about what is linear and non-linear? We'll see that. So we'll continue with our support vector machine. So this is how the support vector machine classifies two data points. For example, imagine we are having two classes, yes or no, like class or 1 or 0. We have a blue color and a green color, and what we can see is we can see a center line which is red in color. It is classifying, or it cuts in the plane and differentiate between these two. That's fine. But I'm having other two dotted lines from here, and we are having the formula also. So what does that line means? What is happening there? We'll see that. So this is how a support vector machine will work. And if you see in the center, we are having a line, right? And that line, the middle line we are having, that is called as hyperplane. So that is actually the plane we are discussing, which best separates the data into different classes. Then what is these lines are called as? These lines are called as support vectors. Support vectors, that's how the name has been given for this as support vector machine. So talking about it, see here, usually it will be like a binary classification. For classification, even though if you have multi-class, once again it is one versus rest, so which means that you are going to have like this, a two class. So obviously the format is going to be like this. So there will be a line which best separates these 2 points in the plane. Fine. So what is this hyperplane is? You will be having one hyperplane for this class, and you will be having another hyperplane for this class. And if you closely watch this, you can find, see here, the hyperplane for this blue color class passes through the closest point which is near to the hyperplane, or which is the nearest point to the hyperplane which best separates that, right? So if you see here in the green side, it is not passing through these points. It is passing through the point which is very close to your hyperplane. So from, for example, imagine this blue color as class A, and imagine this green color as class B. Then the class A, okay, so which point in class A which is closer to your hyperplane, through that your plane will be passing. So that is called as support vector for this class A. Like that for green also, we will be having another plane which is passing, which is the closest point we are having towards the hyperplane from B side. So that will also be mapped, and we will be having a hyperplane which is in the center, and we will be having support vectors. So how the best fit is obtained, etc., I'll tell you now. So imagine this is your data points, okay, it's a classification problem. So you are having two classes, and when you plot your data points, you are having your points like this. And you can ask me like data points, you cannot exactly get some data like this. There is actually a task for that too. That is what the linear and non-linear we are supposed to discuss. We'll see that. So imagine you are having this data, two classes are available, okay. So what you will be doing is you will be fitting a line, okay. So that line should separate these two perfectly. So we all already know, right? So we have seen it in linear regression also, a straight line. So if you want to separate it, or if you want to pass through it in regression, we have done, right? So you can have multiple fits. If you ask me, this line can pass through this or this, the hyperplane can be of any side, right? Not only like this, you can tilt it towards here or in any way. So how does that work? So what will happen is, so that's why they are including something known as hyperplane. So instead of fitting a single line, so we'll be having a line that is will be middle towards your support vectors. Once again, hyperplane is the center line, and support vectors will be, for each class you will be having a support vector. So totally you will be having two support vector. So for this red color class, there will be a support vector which passes through the closest point which is available. So if you have another point here, then your support vector will be passing towards here. So your hyperplane will tilt towards that side. Like that, for our yellow color class, we also have another support vector which passes through that point. So now when you have your support vector, you can have your hyperplane. That's fine. So now you know how our hyperplane is passing and how support vectors or built. Okay, it is just passing through the closest point from each class. So we are having all these three. Now if you ask me, see here, this example, now it will be a really good question for you to ask. Like linear regression, you can have multiple best fit. So how will you decide which fit is best? Because see here, yeah, we are passing through the closest point, but what is this case? This line passes through the closest point of blue and this line passes through the closest point of red. Like that, see here, this line passes through the closest point of blue, right? And here also it passes through the closest point of red. But which is selected? Okay, so you can go like this way, like we have here, or this way. This is like much more broader and this is much more narrow, right? So which will be selected? If you ask me, then the task of this support vector machine is to select, okay, a support vector and hyperplane, or a support vector which has maximum margin. So talking about margin, which is the distance between this line and this line. So the distance between these two will be calculated, and visually now you can see that this is a broader one, this is a narrow one. So obviously this will be selected as a good fit. So your task is to fit a maximum margin. So that will be done by our support vector machine algorithm. You have both classifier as well as regressor. This is for classification. Once again, I'll tell you how it works for regression and all. Yeah. So now if you ask me, okay, this point is good, but whether can you expect the same method or same type of data if you plot when you're in a real world data set? I will tell you it's not even possible. You can't roughly have this very easily. And if some place, this is called as linear data, which is linearly separable with a linear line. But what if your data set is something like this? Can you even separate this? You want to have a hyperplane to which separates best of the two, and you need to have support vectors. Where will you have a support vector here? Think about it. Can I have a support vector here? So I have two classes. This one, this is a class yellow color, this is another class. So I want to pass a closer line which passes through the yellow, but how will I even fit it in this case according to our support vector machine? Blank, right? We don't have any idea how it will work. So what will happen is you have some options in your support vector machine algorithm. So one of such option is to choose the kernel. So kernel is a parameter which you can modify, and there are some parameters. If you use it, what will happen is to avoid or to overcome this linear versus non-linear data problem, because that's what the task, if you imagine our regression problem, linear regression, we had used a straight line. But when we go for logistic regression, we have skipped it and we went for a sigmoid curve. But here, to avoid such problems, for nonlinear problems, we'll be using something known as kernel. See here, when you see it in 2D, you can see these points are like this. But there will be a plane, okay, like it's 3D in any surface. Okay, there can be points which separate these two. See here, when you view it in 3D, it's like, for example, not only particularly in 3D, like some features will help you to differentiate between them. Okay, like in 3D, if you view it, the same thing if you view in 3D, you can see you can create a decision surface here. So anything above that will be belong to one class, and below that will be belonging to the green color class. One will be red, another one will be blue. So in this decision surface, you can have your hyperplane, and to this closest red color point, you can have your support vector, and in green color you can also have your support vector. That's actually good, right? So like that, support vector machine has some options in kernel which you can particularly utilize for handling this non-linear data. So you need to analyze your data too before going into this. Your data is linear or non-linear, or you can go with support vector machine and check your result. If it's not good, you can utilize this kernel parameter. About talking about the hyperparameter like this optimizations and all, we'll be seeing it in day 70. About some introduction about grid set CV or randomized CV, we'll be discussing there. And yeah, so that's how kernel will work, and it will help you to find. See here, we have seen this point, right? So now we can't separate it. So if you use the kernel options, you can able to find, the algorithm will automatically try to find a plane, okay, a decision surface which decides between these two, which will give you your hyperplane and support vectors. From that, you can go with further predictions, right? So that's what one advantage of our support vector machine. It's really perform well when you go with your binary classification. And talking about the math behind. So till now we have seen about how it works. So talking about what is the formula, what is the math happening behind. So once again, its task is very simple. Okay, you want to just maximize the margin between them. So there is actually a formula for this. So if we talk about how it works, I need to tell another story. Please follow through it. So yeah, we are having our optimal hyperplane, support vectors from both sides, maximized margin, etc. So yeah, we'll go from the base. Once again, we are having a straight line, right? Straight line, you know the formula from linear regression, which is going to be y equal to mx plus c. Okay, hyperplane is nothing but a straight line, so it's actually y equal to mx plus c. For now, let us not think about our support vectors. Okay, so I'm having 2 points. One is red, another one is green. Like we had here, we are going to have 2 points. One is red, another one is green. And it is plotted. You can see the value of P1. The point 1 is plotted in the space which is -3 in x-axis and 0 in y-axis. And when you talk about this point 2, it is plotted in the space in 3, which is 3 in the x-axis and 3 in the y-axis. Fine. So we have plotted it. And our hyperplane, imagine, passes through the center. So now what will be the value of C if you imagine? What will be the value of C actually? So C is nothing but the intercept, the line intercept where it reaches your axis y, right? So where this line is reaching your y, it is reaching in the 0. So your value of C will be 0. And let us have our slope value m as -1. Okay, slope will give you how tilted your line is, right? The different. So if you have higher values, it will alter your orientation of your line, the tilting of your line. Let it be -1. Consider that, and let us keep it that. So the parameters, okay, so which is going to be considered in the variable which is w, which is nothing but your value of m and c, and it is going to be in this format. So if your m, for example, we'll keep it as -1 and the c value is 0, so the value of w is going to be -1 and 0. So what the support vector machine do is it uses a formula. It may look complex, I'll tell you. So you have your parameters of the line which is m and c, -1 and 0, right? So you do use a formula which is transpose of this w and dot product, matrix dot product with x. Okay, and here we will be doing it with the next point. I'll show you. So imagine we are having 2 points, right? So we have w. So if you want to apply to this formula, you need to take transpose of it. So w transpose is going to be, you need to convert it in this format, right? So the rows will become columns, the number of columns will become rows, taking transpose. So this -1, 0 in matrix will turn into this format with 2 rows and 1 column, which is -1 and 0. And you want to perform dot product with your x from this point, which is -3, 0. So if you perform dot product, this -1 and -3 will become +3, and 0 and 0 will multiply and become 0. So you want to add it. So total of this is going to be 3 for this point, which if you note it down, it is a positive value. Fine, leave it. Come back to the right side. Now we want to do the same for this point, okay, which is 3, 3. You have the value of w transpose, which is -1 and 0, and take a transpose of it and then go with your x value dot product. -1 into -3 will be -3, plus 0 into -3 will be 0. So your output is -3. So don't consider the 3 value, okay, it can be any value. But if you see, so hereafter when you go with this support vector formula, what will happen is the class which is belong to this red will be a positive value always, okay, if you use this formula. And if you go and see this point, whatever things you have beyond this hyperplane in this side will be having a negative value. So that's how it will differentiate. See here, for all the points which is lie in the left side of the hyperplane, the wt, which is the transpose of w and x value, will be a positive. And if you do the same on the right side of the hyperplane, the points which lie on the right side, you will be getting a negative value. Okay, it's the formula. If you apply, you can check it. So in the left side of your hyperplane, it will be a positive values, the output from your w transpose of x, and on the right side it will be negative values. So we'll be having two classes, one is positive, another one is negative. And this is the formula finally. Okay, so talking about our support vector, if you have a support vector here and another support vector here, your formula will be like this, which is nothing but this W, right? We are discussing, and the dot product with X plus B, okay, constant, and the output is going to be -1 here in the left side. Okay, so your value, when you calculate it, this value will be positive here when it -1. Here it will be negative, so if you have it to +1, so it will be, when a final output will be -1 negative here, it will be positive here. So this is the formula for both. And when you do some basic algebraic formula calculation with these two formula, you will be getting a formula output which is 2 divided by the magnitude of this value W. Okay, so I'll tell you how it is derived from these two. I'll show you in the next slide. So your task is, this is the margin value between these two when you calculate, which is 2 divided by magnitude of this W. Okay, and your task is to maximize this. How much maximum it is, that much good the fit is. That's what our support vector machine do in the math behind it. So this is the calculation. See here you are having two formulas, right? Write down those two formulas and then calculate it. Okay, substitute it and then calculate it. When you go and sum it down, you can see we are taking the B cancels out. Okay, and then this 1 will become 2 here. You will be having with Wx2 minus Wx1 equal to 2. And if you take the common and then divide it with this magnitude of W, so your distance difference between your x2 minus x1 will be 2 divided by magnitude of W, and you should be having this as maximum as possible. So which fit is giving maximum of this value, which is 2 divided by the magnitude of W, and you know the W values, right? What is W value? Which is nothing but your intercept and slope value, M and C value, so that is W. So which line which is giving the value which is high in your 2 divided by this magnitude, so that will be the maximum margin, and that is chosen as the best fit, and that is what the math behind our support vector machine classifier. So I hope this is fine. You guys understood about what is happening behind. Moving with the next one. If you ask me, then what is happening in your multi-class classification in support vector machine, it is going to be 1 versus rest. So if you have your green side, see here in red we will be having these both. So like that, one is taken as one class and the remaining two will be considered as another class. Like that it will be splitted, and based on the probability we have seen with our logistic regression multi-class, same is applied here. It is 1 versus rest concept. Yeah. So that's all about our support vector classifier. So if you ask me about then what will happen in support vector regression or support vector regressor, once again see here guys, regression, what we are having here, we are having a straight line, then actually it's a good task, you can just plot the points, but how will it work? Talking about support vector classifier, your task is to find a support vector which passes through the closest point from both the classes, and a hyperplane which is having your maximum margin. That's it, you will be winding it off, and you can make predictions with that. So if you pass a new value in wherever it is fitting, so based on that the output will be decided either which class it is. But when you go for support vector regression, we will be having something known as epsilon tube. Okay, so if this epsilon tube, which is nothing but the distance between your two support vectors, it's like a tube, and what is the task of it is nothing but you need to find, okay, so the task of it is to fit the hyperplane and the support vectors, which is your positive or negative hyperplane, which is nothing but support vectors, to fit maximum points inside of this tube. Okay, so which orientation or which value from your W, which is going to be, see here once again, y equal to mx plus c, m and c value, m and c value. So when you have it, which fit gives you most of the points inside this tube, inside this epsilon tube, that will be a best fit. And you know regression, so with this straight line you can plot your x and y values and get your output. So that's how our support vector regression works, and the task is to minimize this output, which is 1 divided by 2. If you go with this formula, the value should be minimum. So which is minimum, which fit is minimum, that will be the best fit, which will be covering all the points inside, most of the points. Yeah, so that's all about our support vector machine, how the math behind it, how it works. So if you want to use it, you need to take it from sklearn .svm, the support vector machine. It will be in small letters. You need to import. You can import svc, which you see here. When you import the model, it is given in capital letter. Note it down. And you can search in browser also. If you type the name of it, the scikit-learn library documentation will pop up, and you can know where your algorithm, how to get it. So if you type with svc, which is support vector classifier, and svr is nothing but support vector regressor. Okay. And also, if you check the documentation, we have discussed about kernel, right? So there are a lot of kernel options here. We have linear, which is applied directly for linear. For others, you can go with polynomial and try it, or RBF and try it, and sigmoid is also available as kernels. So if I want to use it in support vector classifier, when I call the algorithm, when I create an object, I will be passing kernel equal to linear or kernel equal to RBF. Okay, you can set the kernel, you can check the kernel and use it for your application. So I'll show you from sklearn.svm import svc, which is support vector classifier. You can also import support vector regressor and use it. Okay, so our next task is to go and create an object. Classifier will be support vector classifier, and you can also have your regressor. This is just model, right? So we have already seen how to use it. So when we do a project, we will be combining everything and go in a flow, starting from the pre-processing step, data collection, every part. Since we are learning this particular thing right now, we will be skipping those parts. And yeah, you can also set the kernel value. You can set linear. You can also get it actually. It is linear. You can also set what all kernels we had here. You can go with polynomial or RBF. You can learn about it in the documentation furthermore about how it works, what is the kernel, etc. So if I want to know what is the base version or the default value, we'll go with our empty support vector classifier. And if I get the kernel, I think it is suggesting me the last, or we can also check it using sklearn support vector classifier. You can check the documentation and you can scroll below. The default kernel here is RBF. So that's what the default kernel is. So if you want to change, you can use linear or the other stuff like polynomial, etc. for polynomial features to find the third layer or the 3D plane, decision plane to decide which they belong to. And these are all hyperparameters. For example, there will be a default value and you have options, and you can optimize that too. That's what we'll be seeing when we see about our hyperparameter optimization later on day 17. Yeah, fine. So we also have support vector regressor, which we can fit and then predict, use it for predictions. So that's all about our support vector machine. I hope it will be clear. And it's time for us to move towards the next big algorithm, which is decision tree. Starting with decision tree, we'll see about it. It is actually a tree based algorithm. So what is tree based and all, we'll see. Decision tree is a supervised learning technique that can be used for both classification problem as well as regression problem, but mostly it is preferred for solving classification problems. And the decision tree usually mimic human thinking ability. It's not like you can use decision tree regressor as well for regression also. And the decision tree usually mimics human thinking ability while making a decision. So it is easy to understand, easy for us to understand how it works. Still, there is actually a math behind it. We'll be discussing that about some calculations like entropy or information gain. So, but this mimics our human thinking ability. Decision trees are common. You would have used in tree-based algorithms, etc. are already available in DSA topics, etc. Not only on machine learning. So it's like yes or no. A branch will be created and it will move, right? So that the concept is applicable here also. So the logic behind the decision tree can be easily understood because it's a tree-based structure. We'll see what it is. So this is how a decision tree will be. So you will be having a root node or a parent node. The parent node is the one who starts. Okay, it's a root node. And you will be having decision nodes. So from that a decision will be made and it will be splitting. And then another factor will be considered and then it will split. So like that we'll be splitting into parts. I'll tell you with example in a data set. So it will be going with the decision node if it has a decision. Okay, decision node will continue to the next decision. If there is no decision else made, then it is actually a leaf node which will be having no more branches. So this is like a root which will be creating a tree. Okay, and a tree will be having multiple branches. Branches can branch, but a leaf cannot branch, which means the end is the leaf. In between, if you have branches, it is actually decision node. So this is actually a common example to teach decision trees, mostly used in many books. We'll see. This is actually a data set and it's a classification data set. And the feature here is weather, temperature, humidity, wind, and your target is play. So the play is nothing but yes or no. Whether based on these conditions you want to predict, okay, whether you can go and play or not. That's what the question is. And in weather we have sunny, cloudy, rainy, some classes there. In temperature we have some conditions. In humidity we have some. In wind we have some. Now, see here, now I want to go and classify this. For example, it's not like we'll be starting with weather. That's what we'll be seeing later when we see about the max behind it. But see, starting with weather, I'm choosing weather as the first condition. So now, if I go and narrow it down, when the weather is sunny, okay, so there is no here. Okay, fine. When the weather is sunny, we are having sunny here and the play is yes, which means that the leaf hasn't been obtained here. Okay, there are still branches. So I'll be going with the next step, which is I can go with humidity or temperature like that. So I'm checking humidity. Sunny and high, play is no. Okay, sunny and normal, play is yes. See here. So we can go and check the next one. Sunny and high, play is no. So these two matches, right? Sunny and humidity is high, the play is no. Here also the same. So if my data is having the same thing, then actually it reaches the leaf. Okay, if it's normal, it is yes. So that's actually a leaf node. So like that, if you talk about cloudy, when you have cloudy, the play is yes. Okay, here the cloudy, play is yes. So based on my data, I can see in all the places where the weather is cloudy, the answer is yes. So that's actually a leaf node here. So if you go with rainy, you have branches. So you'll be going with further features. So still if you don't obtain it, you will be going with further more features. Like that, trees decision will be made and branches will be made. Finally, you reach decisions or leaf nodes. That's how a decision tree works. This is another example, like a question based example, which is actually a guess the animal. I took this from a book. So it is like a question, guess the animal from a decision tree. So the question asked here is, it's like a human thinking capability. See here, more than 5 legs. So okay, we are going to predict something which is an animal and your task is like, it can be animal or insect, don't worry about it. Because the more than 5 legs, no means you can go towards that side or yes means you can come towards this side. We'll go with yes. Okay, it is having more than 5 legs. So it is hiding under your bed. Okay, so if it's no, then you go with making honey. Okay, so if it's no, then it's a mosquito. Okay, you can see mosquito don't make honey, it can hide under your bed. Okay, so it can have, I don't know exactly about the legs, they are given here. Okay, so talking about makes honey means it's a honeybee which can be under your bed and it can have more legs. Fine. Talking about this star of Charlotte's web, okay, whether it is build good webs, whether it's a bed bug or spider, you can decide with that. If it's less than 5 legs, then it's delicious, which means whether it's a eatable one. Okay, so if it's a yes, then it's going with the next few categories. Okay, like that the algorithm decides with your target variable and then go step by step till it reaches all the end, so that with that it can learn. That's how a decision tree works. So talking about the math behind it, we need to understand once again. See here the parent is weather and the children are humidity, wind and temperature columns. Now if you ask me whether should I go with weather only or can I start with temperature, which will be good, or after temperature, or see here, even though I start with weather, I directly go into humidity. Can I go with to temperature first and then go into humidity, or can I go with wind first and then go with the next one? These are some of the questions. Okay, so how will a decision tree decide who is the parent node, who is the next set of children, etc.? Actually, all type of combinations iteration will be happening behind. So what will happen is, So that can be obtained with the help of this entropy calculation. If you talk about entropy, even though in chemistry the formula is, it is a measure of disorder or randomness, how random it is. So in order to build a decision tree, we will need to decide what questions to ask and in what order. You don't know what questions to ask based on the features you have, but in which order are you going to ask the questions? That's actually a big question. So in such place, we are using this calculation, which is entropy. It is a concept used to measure the impurity or disorder of a set of data points within a node of a decision tree. And when building a decision tree, you want to minimize this entropy value. So wherever, I'll tell you how entropy is calculated. If your entropy value is less, then actually it means that it's actually a good fit. So the idea is to find attribute values or features that when used for splitting results in nodes with lower entropy. Okay, you want to reduce the randomness. Okay, so that will give you the best fit. So that's what entropy is. To calculate entropy, this is the formula which has been used, and in max term this pi, okay, p1 p2 etc., this is the proportion of data labeled as class ci. We defined it as entropy. We'll be taking this value from our calculation from decision tree. It will be done in the back, and log to the base 2 will be taken for this value and their multiplication, and they will be subtracted, and finally we'll be taking a sum of this value, okay, pi log 2 of pi. So with this entropy can be calculated. For example, this is another data set which is having a feature, for example, the same play, golf, okay, yes or no. So based on it, the entropy will be calculated, for it a value will be obtained. Like that, see here how it is calculated. We are having yes 9 times and no 5 times. So the entropy of this 5,9 will be, the formula will be applied. Okay, this is the percentage of them. Can you see it? I'll tell you what is this P1 is, which is the proportion of the data. See here, don't get confused. I have two classes here. It can be further classes. We'll be adding it in the formula when we have it. 9 and 5 is there. So the probability of 5 is 0.36 and the probability of 9 is 0.64. So when you apply this to this formula, for 0.36 it is 0.36 into log to the base 2 with 0.36. Similarly 0.64 we will be applying here, and you will be subtracting it. The summation will be taken. Okay, sorry, this is also a negative value, this is also a negative value. See here, summation of this negative thing. So this is also a minus is there, here also a minus is there. So the total gets added, it is coming around 0.94. This is how this value, entropy, is calculated. So like that, what we'll be doing is, with this entropy value, we'll be going with another formula, that is information gain. Please follow this. Now you know how to calculate entropy. After getting this entropy, what we will be doing is, we have a parent and children concept right here, a parent class and a children columns. So like that, for every combination of parent and children, using this entropy for each, we will be calculating an information gain. Information gain is another important concept related to entropy in decision tree, and it quantifies the reduction in entropy achieved by a particular split. And the formula for information gain, or this value information gain, is entropy of your parent. You know how to calculate the entropy of the parent, right? You can pass your parent here, which is, for example, if it's a weather first time, then temperature you can calculate for everyone. Okay, you will be calculating information gain for one by one, minus the weighted average, the summation of all the children entropy. So that will be calculated. So okay, like that, for every features you are having, this will be calculated, and this entropy, you know, right? If you will give it inside, you will be getting value, and when you subtract it with your parent class, you will be getting the information gain. And decision tree algorithms typically select the split with the highest information gain, as it represents the most effective way to reduce uncertainty or impurity in the data, which means your entropy should be very low. Okay, but if you want to have entropy very low, then the information gain should be high. Okay, if the information gain is high, which means that your entropy value is very low, which means the decision tree algorithm typically select the split. Okay, it will calculate for every possibility and select the split which has highest information gain, which means it will be having lowest entropy inside of it, or lowest uncertainty or impurity inside of it. So this is the formula for your information gain, will be the parent minus the summation of the parents, summation of the children entropy. For example, this is the calculation is happening, and the weighted average, this is how it will be taken. So from the total, it will be calculated. 17 is the value here in the children here, 13 is for him, total is 30, so divided by 30 multiplied by the value entropy. Here 13 divided by 30 multiplied by the entropy value of child 2, that will be calculated, which is 0.615. So the information gain is going to be parent entropy minus this weighted average of children. So this total is information gain. Like that, for every parent and children combination, we will be getting a gain value. See here, with outlook as parent and these as children, we are getting the gain as 0.247. With temperature as parent and remaining as children, we are getting 0.029, and like that we are getting these values. So in these four values, tell me guys, which should our decision tree algorithm select? You can give the answer. Which should it select? It should select the highest gain value, right? Where the value is very high, it should select, because it will have the lowest entropy. That will be a good fit. So the gain value is high here in our outlook. When you go with outlook as a parent, so that will be selected. Highest gain is taken, and they will be subtracted till your last leaf node in all the place. It will be done. This is what is happening in a decision tree algorithm. And yeah, so that's all about decision tree classifier. You can have binary and multi-class classifications. That is actually good. And this is how the best fit is selected. And you know, like answering these questions, once you got the best fit, by answering these questions, the output will be selected. So if you pass a new parameter, it just want to pass the yes or no one by one, so that the output can be selected from that. Yes or no will be selected from that. So that is how a decision tree classifier works. Okay, once again, you can have decision tree regressor also, but in the first itself I have told you decision tree is not actually preferred for regression. You can do that too. So when you go for decision tree regressor, here you don't have any classes like this, right? So the output, how it is calculated is, there is something known as mean squared error. This mean squared error is nothing but, I haven't told you this term. We'll be seeing this term particularly when we discuss about our metrics in our day 17, which is how to evaluate your algorithm. For regression, when we see about linear regression, what we have done, we need to find a line which has the best fit, which has less error, which means the summation of the error. Okay, so when you have the mean value of your error, okay, if you calculate the error, that is actually mean error calculation. So when you get the error, if you square it and take a mean of it, that are actually nothing but squared value of it, which is nothing but mean squared error, which is MSE. And when you split it, the idea of this, the decision tree regressor, to find the best fit is to get a line. Okay, so get a split which has very less mean squared error, which means low error, and it should find in which order, if it splits, it has the less error in the output. That will be preferred, and that will be given to the next set of nodes, and that will be taken as our parent and children node. And that's all about our decision tree regressor. And you can have these both from sklearn.tree. So it's a tree based algorithm under this package, which is tree. So from sklearn.tree you can import decision tree classifier, and from sklearn.tree you can import decision tree regressor and proceed with that. Yeah, so I'll tell you how to go hands-on and import it. From sklearn.tree you can import decision tree classifier. See here, the name starting letters will be caps. If you don't go with it, you will be getting error of not finding the particular thing. Decision tree regressor is also available. And with that, you can actually create objects for classifier and regressor and use it in your algorithm. All these max things will be done behind your algorithm, but you need to have what is the idea of what is happening behind to be a good machine learning scientist, and it will help you a lot in the interviews also. Yeah. So continuing with the next one, we'll see the rest of the algorithms, which is ensemble algorithms like random forest, AdaBoost, XGBoost, and naive Bayes, k-nearest classifier, and the clustering algorithm in the next session. So in this session, we have seen about two important algorithms elaborately, which is support vector machines and decision trees. And I think totally in the last two sessions, we have covered linear regression, lasso, ridge, logistic regression, and then support vector classifier, support vector regressor. decision tree classifier and decision tree regressor. So we'll see the rest of the algorithms in the next session. Thank you.